All right, guys, how we doing? Coming at you here with the first lecture video for chapter 16 here. Now, redox chemistry, right, is the is the name of this chapter 16 here, right? Redox reactions in electrochemistry is kind of like the title of chapter 16 here. And a lot of this has to do with a lot of the science behind batteries and how batteries work. And a lot of what we do here, guys, is always going to be talking about the conversion between chemical energy and electrical energy, whether we're going from chemical to electrical or from electrical to chemical and kind of everything in between as well, right? So a lot of this is going to be rooted in the idea and concepts surrounding batteries. Okay, so we're going to be talking about redox chemistry, which is a basic way of saying reactions in which electrons are transferred from one atom to another. So we're back to talking about electrons, right? A very long time ago, back in probably September, October, we sort of had a conversation about the three different subatomic particles that are present inside of atoms for certain elements, right? Or all elements, rather. We talked about protons, we talked about neutrons, and we also talked about electrons, right? And I mentioned that of the three of these subatomic particles, easily electrons are probably the most important. And here they are once again, kind of coming back to haunt us, once again with this chapter 16 here on redox chemistry. These types of reactions are also known as oxidation reduction reactions. It's kind of where you get the word redox from, right? The first three letters, red, being R-E-D, read, comes from the word reduction, R-E-D, reduction. And then the O-X at the end of redox comes from the ox, or O-X, from oxidation. So these are oxidation reduction reactions, aka redox reactions. And more specifically, guys, each of these words, oxidation and reduction, refer to what's happening to our electrons in response to these types of reactions that we see occurring here. So whenever we have some substance undergoing oxidation, it's a representation of that substance losing its electron. So if it undergoes oxidation, it loses electrons. Now the opposite of that, if a substance is gaining electrons, that means they're undergoing reduction. Now that might not make a whole lot of sense right here. Obviously reduction usually tends to mean we're losing something. If I'm reducing something, I'm losing it, or I'm lowering it, and yet somehow we're gaining electrons. Kind of a funky concept, but the idea of reduction refers to it's a reduction in the charge, right? It's a reduction in the charge. If I'm gaining electrons, guys, electrons are negatively charged. If I'm gaining a negatively charged substance, my charge overall is being reduced or going down into the negatives. And that's kind of where that word reduction comes from. Now, oxidation numbers and how to assign them. This is pretty much straight up review, guys. We spent a lot of time doing this exact same thing way, way, way back in chapter 5, right, talking about ionic compounds and ionic bonding. But, it kind of had a different name, right? Kind of have a different name to us. We just would refer to it as the charge of that substance or the charge of that ion, whereas, the actual real name is the oxidation number or oxidation state. So, the charge that we've always talked about, right? Na having a +1 charge to it, that's actually just called its oxidation number, +1 being the oxidation number. So oxidation numbers show the charge or apparent charge on a monoatomic ion, and they can be assigned for ions in ionic compounds or for atoms in covalent molecules and compounds as well. And on the next slide here, I'm going to show you all the rules for, assigning oxidation numbers as well. And sometimes, they're referred to as multiple different things, right? Whether it's oxidation number, oxidation state, straight up just charge, right? Charge is a little bit outdated, but again, oxidation number, oxidation state is going to kind of be the new phrasing we use going forward here, right? So what are our rules for assigning oxidation numbers? It's pretty simple, guys. Again, this is going to be pretty much straight up review here. Any pure elements are going to, of course, be 0, right? So if you take a look at anything on the periodic table or on your reference table's periodic table, any of those pure elements on the periodic table that have not either gained or lost an electron are not considered ions, so therefore they don't have an oxidation number or an oxidation state. They're just going to have essentially a charge of 0. F, right? Fluorine, always going to be -1. Again, this is all review here. Group 1s, all of our group 1 elements on the far left, right? So if you've ever looked at my periodic table in the front of my room, guys, all the red elements on the far left in group 1, your NAs, your lithiums, your rubidiums, any of those guys there, right? Those are going to be +1s. And if your group 2s, the ones on my front reference table that are all in orange there. So beryllium, magnesium, strontium, calcium, right? Any of those guys in orange up front are always going to be a +2. oxygen is usually a -2. Right now, this is where the phrasing changes. Instead of having it being an always case, there sometimes are usually cases, right? So O, oxygen, is usually a -2 charge, except when there's a couple of scenarios here. Except when oxygen is being bonded to fluorine here. That case, oxygen is instead going to actually have a +2 charge. And also, in certain instances, when oxygen is bonding to hydrogen, creating peroxide, right? H2O2. So, in that case particularly, oxygen ends up having a -1 charge. So again, oxygen is usually 95% of the time going to have a -2 charge. There's only two very, very specific scenarios where it doesn't. And those are the two right there, right? Hydrogen is usually a +1, right? Our guy at the very, very top left-hand corner of our periodic table, right? The very first element on the periodic table, capital H, is usually a +1, all right? The only time that it's not, guys, is when it's actually bonding to any of our group 1s, which are always a +1. So if this is a +1 bonding to something else that's a +1, those are not going to bond. Those are not going to mesh together, right? In order to balance out a +1, you need a -1, right? So if hydrogen's going to ever bond to anything like sodium or lithium, right, it definitely needs to have a -1 charge instead, okay? Also, our halides, right, all the way over on the far right, group 17, so things like fluorine, chlorine, bromine, iodine are 4 halides. Group 17s are usually going to be a -1. Sometimes they have a variation of what they, more than just -1. If you ever take a look at the periodic table, right, you see things like chlorine and bromine. They've got like 5 different charges, right, present there. So, but again, they're usually a -1. But sometimes, very rarely, there are going to be some of the other charges that are listed on the periodic table there. Okay. Now, how do we go about assigning oxidation numbers? Again, this is all review, so I'm going to go a little bit faster here. Again, always start out with what you know. Any of our always cases that are here, right? So if you see fluorine, a group 1s, a group 2s, you're always going to assign your known oxidation numbers. Okay. Then you're going to assign things that are usually true from the table on the previous slide as well, right? So our usuallys, so our oxygens, our hydrogens, our halides, right? Things that are usually true. And then it's going to be your job to calculate the other oxidation numbers. And obviously, when I see you guys in class next, we'll be able to do a handful of examples just to kind of, get back into the groove with this stuff here. And then ultimately, guys, the most important thing when it comes to assigning oxidation numbers, the sum of the oxidation numbers should add up to 0 for neutral compounds. So if you are creating or writing down a full formula for an ionic compound, right, not just an ion, right, not even just a polyatomic ion, but for a neutral compound like NaCl or anything like that, MgBr2, right? Those neutral compounds need to have all their charges add up to 0, right, because they're neutral compounds. Again, a little side note here, right? I know I mentioned polyatomic ions a minute ago. If you're running into a situation where you're talking about a polyatomic ion, let's say you're talking about the polyatomic ion hydroxide that we just spent a lot of time talking about, right? OH-. Sometimes, guys, OH- is going to have, I shouldn't say sometimes, all the time, hydroxide is going to have its -1 charge. That means the O and the H need to bond together to form in a -1 charge. So the polyatomic ion is going to have its charge add up to exactly what its charge is. Okay. Now, getting back to talking about these redox reactions here. Again, they're a type of chemical reactions that involve a change in oxidation number, right? So this oxidation number that we know and love, that's in the top right-hand corner on our periodic table, guys. Again, this is where we're going to start to flex our knowledge talking about those particular ones, right? Because oftentimes, a lot of these elements in the periodic table, when they are ions, they have multiple different charges. They have multiple different oxidation states. And that's where this stuff comes into play here. It's the change in the oxidation number associated with that particular ion, okay? And again, it reflects the transfer of electrons whenever there is that change in transfer of oxidation numbers. Again, remembering that oxidation is the loss of electrons, whereas reduction is the gain of electrons. And I've got this little image here to kind of help you remember it, right? Thinking of all the different times that I've shown you different types of acronyms and images and whatnot, and sayings and phrases to kind of help you remember stuff yet. Right here, we've got the sentence, or I guess the phrase, the words here, oil rig, right? So the word oil in RIG and rig is going to help you try to remember exactly what the definitions for oxidation and reduction are, right? In terms of what's happening to the electrons, right? So for the word oil, O-I-L, we've got O for oxidation, I for is, and L for loss of electrons. And then for rig, R-I-G, we've got R for reduction, I for is, and G for gain of electrons, right? So oxidation is loss of electrons, reduction is gain of electrons, giving you oil rig, right? So again, the first letter of each one of those words is going to give you exactly what's happening to the electrons for those specific things. You have to know these two definitions, okay, like the back of your hand, guys. It's really important you know and understand the difference between oxidation and reduction in terms of what's happening with electrons. And again, this mnemonic device here, oil rig, is going to really help you out in this case particularly, okay? So please make sure you spend some time really thinking about this. And obviously, like everything else, we'll talk more about it in class and kind of explain some more things, so don't fret too hard. Now, all this stuff kind of lends itself towards this idea here of doing what we call writing half reactions. This is going to kind of be one of the initial stages towards writing a full redox reaction, right? So we have to kind of start a little bit small here, just writing half reactions, because then we can take this and build up on it going forward. So first things first, you have to do your best to identify the correct oxidation states for any of your substances, right? That's number one goal here, identify oxidation states. Number two, identify substances containing the same atoms, right? So if on either side of the chemical reaction, you've got, let's say, magnesium on one side and magnesium on the other, you have to make sure you can identify and match those two substances up, right? Because Mg and Mg are both magnesium. So same deal, right? So, make sure you can identify substances, number one, based on their atomic symbols, and number two, be able to match them up and say, hey, just because this is Mg, with a charge of 0, and this is Mg with a +2 charge over here, it's still magnesium on both sides, right? So we have to be able to match those same substances together, okay? Number three, write two reactions, one for each set of atoms. Again, there's only ever going to be a situation, guys, where we've got two different substances we're identifying. So if we've got magnesium on one hand, maybe we'll have oxygen on the other, right? So these are our two different substances we're working with, and you're going to write two different half reactions in order to do that, right? So the important part here is to recognize that two half reactions make up one full reaction, and that's going to kind of be our end goal as we progress through the beginning stages of this chapter here, right? So we're going to write two different half reactions in the hopes that eventually we're going to take those two half reactions and put them together and make one full redox reaction. And again, each of those half reactions are specific to the elements we've already previously identified, right? So if we've got magnesium and oxygen, we're writing one half reaction for magnesium and one half reaction for oxygen separately. Then we're going to do what's called adding our electrons. Okay, and we're going to add them to the same side that the positive charges are on to balance out. This isn't going to make a whole lot of sense right now. Obviously, when it comes to listing out, steps to do something, it's not always easy to kind of see and just listen to me talk about the steps, right? It's way easier to do an actual example of them, which of course we'll do plenty of examples of these when we are in class next. But again, for right now, just kind of take what I'm saying and we'll apply it soon. So yeah, again, number 4, add electrons to the same side as the positive charge. And lastly, you're going to label each side as either the oxidation or the reduction half reaction, because that's going to be an important little thing that we have to know how to do going forward. Okay. Now, one of the last things we're talking about today is known as an oxidizing and reducing agent. The substance that loses electrons is oxidized, right? Oxidation is loss of electrons. That means, obviously, then the opposite of that is reduction, which means the substance that gains electrons is reduced, right? Thinking about oil rig, OIL, oxidation is loss, reg, RIG, reduction is gain of electrons, right? Nothing different here, nothing new here. But there's this concept known as the oxidizing and reducing agents that kind of flip things on its head a little bit, okay? Because the oxidizing agent is the substance that causes reduction. It essentially brings about oxidation by being reduced. And the reducing agent is a substance that causes oxidation because it brings about reduction by being oxidized. Now, I totally get that that is a little bit confusing. I totally understand that. And again, once we do some examples in class of this, it's going to make a lot more sense. But for right now, just hold on to these definitions here. Again, the top two should not really all be that confusing or different, right? It's everything we've been saying since the start of this lecture video. Oxidation is loss of electron. Reduction is gaining of electrons, right? So oil rig is still very much present in these first two bullets here, but these these ideas of oxidizing and reducing agents are a little bit confusing, and I'll look to flush those out with you guys whenever I see you next in class. Again, this is confusing. All right, so don't freak out too much on this. I'll do my best to kind of flush this out more next time when I see you guys in class. All right, thanks so much, and I'll see you later.